So the environment that you see, is a Wolfram notebook. So in this notebook, you can type text, you can have like, your code in Wolfram language, you can have, visualization, literally, you can have everything. So it's an integrated environment. Uh, so first thing is that, like, as you may know, like, Wolfram Mathematica, it has more than, 6,000 building, functionalities. Each of those functionalities, they are for a specific core area. I don't know, calculus, algebra, like, machine learning. And then, like, very recently, since last year, like, we have been working on, like, developing a collection of functions for doing any sort of quantum computation in a finite dimensional space. So one more time, like, it's any quantum computation in a finite dimensional, Hilbert space. And what we call it is basically is a packlet. So packlet is basically like, a collection of functionalities that are, interconnected. And after installing the packlet, you can have access to all of those functions. So first step, like, you just need to evaluate, like, this code to get what we call as Wolfram Quantum Framework. And as of now, like, these are the list of functionalities that we have supporting any quantum computation. The beauty of, like, having packlet is that, like, then very similar to any other function that you have in Wolfram Mathematica, like, you see here, like, if you click, on that, you would see, like, the documentation page. So each of, like, these functionalities, they have their own documentation page. And like any other documentation, like, the format is the same, like, basic examples, scope, properties, and, like, you can find, other, for example, I don't know, this is the list of, functions that we have. You see, like, basis objects, manipulation of that, entanglement, circuit. So that's the collection that we have. So, like, after installing the packlet, like, it's like you have those, 20 something, like, quantum functionalities with the corresponding documentation. We did our best to have a documentation with no issue, but there might be, some minor issues. Like, if you spotted anything, please let us know, and we would correct that. It's like, the main purpose of this session is having an introduction to quantum computing using our framework. So I'm going to start with something very basic. At the very fundamental level, the way that we deal with any quantum computation is like this. Within some process, whatever that process, like, we are going to discuss about that very soon, but, within a process, what we do is, at the very end, we prepare a quantum state. And that quantum state is stored, like, in one or many physical systems. In quantum theory, the simplest system that we have is a system of, dimension 2. Basically, that's a system that, like, in the simplest case, you can describe it by a vector of 2 with 2 amplitudes, and those amplitudes, they can get, like, complex numbers. They can be pure, they can be complex. Like what you see here, like, let's say that, something happened, and at the end, like, you prepare, like, this quantum state. Okay. Quantum state, like, after evaluating that, like, quantum state in a framework, like, is an object. And this is basically the, like, the summary box, for that object. Don't be scared of, the summary box. Like, if you want, like, we can look at the traditional form. On Mac, the short key is Command Shift T. So, like, that's basically the bracket notation, the traditional form. Okay, so I'm using, like, the short key, or you can simply, like, wrap it around, traditional form, and you can see it, like, that short key was literally, like, applying this function on that state. The beauty of, like, this object is that, they contain lots of interesting information that it can help you to get, like, to have an idea, like, what you're doing. Like, what is the picture? What is this state? It's a pure state form, anisotropy is, 0. It's one physical system, the number of qubits, dimension, etc., etc. But anyhow, like, let's focus on the big picture. So, a physical process happen, like, we prepare a quantum state, and then the next step that we do is we do measurement. Remember, like, in quantum theory, measurement is very different from any other transformation. So, like, whatever transformation, whatever process that is happening on quantum system, measurement is different. So what I'm doing here, And think about it like, very similar to like other functionalities that we have in Wolfram Mathematica. A function, it acts on another function, and then the results is an outcome. So here, like, our quantum measurement acts on, basically, this is the input for this function. I'm saying that, like, measure it in, computational basis. There are some details, like, for example, if you do not know, like, how to do that, like, just look at the documentation. So this is the documentation, and, like, it contains all the information that you need regarding that function. But anyhow, let's again, like, let me just briefly review, and then I'm going to go into the detail. So a state is prepared, and then at the end you do a measurement. In our framework, because, like, we have all other functionalities in Wolfram Mathematica, you can calculate the corresponding probabilities. Remember, quantum theory, the best description at the end is giving you with what probability you can get the corresponding outcome. And this is what we get out of, like, this spatial state. Okay, so, like, that's basically the bar chart of, like, that measurement. That's not what is happening in practice, because these probabilities, like, Wolfram Mathematica, it calculates them exactly, meaning, because we have statistic probability functionality, these are the exact numbers. In reality, like, in experiment, just let me show you, like, a spatial case that I have simulated an experiment. You have to basically repeat the measurement, and you would get a collection of results. Okay, so in this very spatial case, what I'm doing here, I'm simulating the measurement results, and I'm saying that do it 20 times. Okay, and this is basically what I'm getting here. And then, like, out of that, you can calculate the corresponding frequencies. So what I'm doing here is, let me just show you the steps. I'm just telling, like, okay, count them. There is always an association. It says, like, for 1, you got 18 results. For 0, you got 2 results. And then the next step, I'm just saying, like, normalize that based on, like, let me just use this syntax, which means, like, take this outcome. Here I'm just saying that normalize by total, because I want to get the probabilities. It's just like how to get the probabilities. This is basically the frequency that we get. This is what happens in experiment. Of course, like, in reality there are noise and many other complexities, but anyhow, like, that's what you would get. And you can, like, compare them together easily. Like, the orange one is, like, the exact, like, that's exact calculation, and the blue one is what you get out of the experiment. Um, Please note that, like, because again, in Wolfram language, we can have symbolic calculation, and again, all of those statistics and probability functionalities. The results that we calculate, I know, like, I refer to them as a sort of, like, simulation, but they are exact. That's why, like, on purpose I put it, like, as exact. And this is a very unique feature about our framework. Like, if you want to reproduce, like, the measurement results in other quantum frameworks, the best they would do is they run it a couple of times, I don't know, 1024 times, and they just tell you, like, what counts for each measurement. This is the core idea of, like, any quantum computing. That's it. Okay, like, it's prepare a very particular state and do a measurement. And for the measurements, at the experimental level, we get, like, a collection of results. And then based on that, we want to do a very particular, computation. That's it. The biggest headache is usually, like, how to prepare a very particular state that is suitable for a very particular goal, for a very particular, like, objective that we have, and how to prepare that. Okay, so that's the whole idea of, like, developing a quantum algorithm for a very particular purpose. Okay, but let me just comment a little bit more about, like, quantum measurement, because remember that in quantum theory you can do quantum measurement in many possible ways. For example, the previous example that I showed you was, let's say, like, pretending that this is a simulation of an actual, like, quantum processing unit. It was in computational basis 0 and 1. You can change that basis. You can do it, for example, in Pauli X, and you would get the corresponding probability. So these are the results in Pauli X, and this is the result, like, in for, like, computational basis. So that for that measurement you have lots of freedom. Okay, so that's the big picture. A quantum state, you would do a measurement, and for a measurement, like the best is like you can calculate some frequencies, and then you have to ask, like, okay, what I can learn out of those frequencies. Okay, what kind of operation I can do with that. So first, what quantum state? Given like any initial state, like let's say that you prepare your system in a particular state, and then you want to transform that state. In quantum theory, this transformation can be done in many different ways. Okay, for example, like one possible way is doing it in a unitary way. This is what we usually have as quantum operator in quantum theory. So what I'm doing here, I'm just saying that okay, prepare a very particular state and then apply like Pauli X. Pauli X, in 2 dimension is is literally the same, like not operator. And of course, I'm sure you guys know that, like you go from 0 to 1. So this is the transformation, like I'm showing you the simplest case, but like then the next step for any quantum algorithm is, what is the collection of transformation for a very particular objective, what we can do, like how we can compose a very particular transformation. So let me focus on like the idea of like transformation, like how I can change the state. Just like a common terminology that we have in quantum theory, because again, like the most popular quantum systems are quantum system in 2 dimension, like spin half system. For example, like let me show you like a case that I'm preparing, like a random pure state, and I'm just looking at the amplitudes. Okay, so this is literally like uh, for this basis, this is the amplitude, and that's the other one. This is basically the same, like for example, in our framework, the another term that we have for that is a state vector. But you see, like behind the scene, for us, a state vector is a sparse array. And if you want to see like the actual form, just like look at the normal. Okay, so that's what you get. Of course, when you're looking at this state vector, remember like the order, like this amplitude correspond to what element of your basis. Either if you don't know that, for example, look at the amplitude, because it shows you like the keys here are basically like the element of the quantum basis that you are using. But anyhow, like so for the simplest quantum system, we can describe it by a vector of 2 elements that can be like complex. Another way of representing that is by a vector in 3 dimension, and this is what we usually call as a block vector. Each of these objects that we have in our framework, they have a long list of properties that you can find in our documentation page. Like oops, I went to the documentation for. Let me just show you the documentation page here, and if you click on the details, like there is an explanation here, like for example here, block spherical coordinate, coordinates of the computed block Cartesian, like so it gives you the Cartesian coordinates. So this is basically the Cartesian coordinate, and this is the spherical coordinate of r, theta, and phi. And this is basically the 3-dimensional visualization. So you have a sphere, and like this vector represents the same state as what we have here. This representation is very popular. Like those of you, if you want to work like in this field, you need to know more about like Bloch sphere, because this is one of those knowledge, like many times when we want to describe anything, we refer to the Bloch vector and what happens to that. Okay, now let us focus on a very simple case. Okay, so what I'm doing here is that like I'm preparing like a quantum state in a 0 state. I guess you already noticed, like I haven't mentioned that, but look at here, like the quantum state is taking a string as an input. So this is exactly the same as doing it as a vector when the first element is 1. Sorry, and the second element is 0. So this is by definition, that's how we define like a 0 state. And as you notice, like all other functionalities that you have in Wolfram language, like you can apply it on the top of quantum objects. But anyhow, let us continue like with our story. So what I'm doing here, I'm just doing a simple transformation. I'm saying that like this function which is a rotation with a given, the vector is acting on that initial state, and that initial state is basically your zero state. And then I'm looking at the block plot of that state. We can just, wrap it by manipulator, and you see here, it is clear, it's the rotation around the y-axis that we have here by corresponding, angle theta. Okay, so it's just a simple transformation. Now let me make a composition of these operations in two steps. I'm gonna say first step, I'm gonna apply rotation, and you see here the notation that I'm using here is a functional notation. Here I'm just using the prefix notation. Okay, it's just different syntaxes that we have in Wolfram language. But anyhow, what I'm doing here, I'm just saying that first apply rotation around y by the corresponding angle theta on this initial state, and on the result apply rotation around z. And as you can see, for example, this is the rotation around y-axis, and now a rotation around, z-axis. We can go from a final state, we can go from an initial state to a final state. So the idea of a composition, this is what we usually call as a composition, two transformation apply on a particular state. This is basically the very fundamental idea of a circuit. So whenever we talk about a circuit is literally a collection of different operations, and those operations I'm on purpose I'm saying operation in the most generic term, because they can be even non-unitary, non-trace preserving. They can be anything. It can be a noise, it can be stochastic, it can be a quantum channel, it can be literally anything. But here I'm just considering a very simple case, exactly the previous situation, that first rotation around y, then rotation around z. Now this is basically in language of circuits. The most common thing about the quantum circuit is the corresponding visualization, which is what you see here. Each vertical wire, each horizontal wire, it represents a quantum state, and each of these boxes is basically your transformation. And here we should read it from left to right. Okay, so it means this guy here, a rotation around y, it acts first, and after that z. So remember, I'm writing it here, left to right, and that's the very first operation that is happening. There are some, the way that you can build your circuit. I'm gonna show you, some complicated examples. But anyhow, either you can literally, the way that I'm doing it here, include your objects. But you see here, somebody would say, look, this is redundant. I'm just repeating, quantum operator. Can I get rid of that? Oh yeah, of course, we can do that. We also support those shorthand notation. So basically, literally, whenever you have quantum operator wrapped around that, you can just remove that, and that maybe helps with writing the code or reading that. So it's basically rotation around y by the corresponding angle, rotation around z by the corresponding angle, and you can easily again check that they are the same. These two are the same thing. One very important feature of Wolfram language is that you can do symbolic computation. As you can see here, this circuit is a symbolic circuit. I'm not assigning any value to parameter theta and phi. Okay, they are literally like a symbol. And what you can do is you can say, okay, this circuit, now I want it to act on an initial state. So the way that you can do it is just act it that circuit, I call it comp, and it can act on any quantum state, whatever is that quantum state. Okay, for example, this is a state representing 1 qubit, so you can go even with a random q or whatever state you like. Many times we prepare all of our qubits in the ground state, meaning all of them are in the zero state, because that's the most common way of dealing with quantum systems in quantum computing. One shorthand notation is just don't give any input. Whenever you are not giving any input behind the scene, what we do is we are going to set whatever quantum system that you have, all of them at the ground state 0. Okay, so basically this operation that you see here, quantum state 0, and then like this circuit acting on that is the same as this operation. But anyhow, like this is a transformation, like a transformation of the state, and then you can look at like the amplitude, and these are the amplitudes that we got. As you can see here, these amplitudes are still in the symbolic form. Okay, like this is one important thing that to remember about like Wolfram language. It has a very strong feature. Maybe the characteristic trait of like Wolfram language is that you can do symbolic calculation. Okay, now so let's jump, like let me give you more information about like okay, this composition of operation, which is basically the wrapper around them is our quantum circuit operator. You can do whatever you want. Let's try to read it. Like so here I'm just saying that poly x, poly y, and then rotation around x by the angle theta. And this is basically the collection of like gates that we have, like like that's how we would call them in quantum computing, and all of them are acting on the same wire on the same quantum system. A very interesting feature that we have in our framework is called order. So you can say, you can specify a very specific order. You can say, look, I want this rotation to act on the second quantum system. Okay, so that's how you would do it. You would just specify a rule, and this time you would say, okay, this rotation goes to the second system. And if you look at like again, like what I'm doing here, I'm just using the shortcut for traditional form, like on Mac is Command Shift T. And as you can see here, like so x is on the first, after that y on the first qubit, and then like you have rotation on the second one. Remember, like unless these commute, like the order that you are writing them, like is very important. So that's the rule of thumb. Like those of you who are new to this field, remember, like the order that you're writing all those operations are very important. Or another example, like look at this example. What I'm doing here, I'm just saying that okay, this time, like I would like poly y to act on the third qubit. So this time we are gonna have three wires. For the first one, we have like poly x, second one rotation around x, and the last one is y. So that's how like we can build a composition of different gates, different transformation for our quantum systems. Of course, the examples that I have shown you so far, like all these examples, as you see, like each of these transformation, they are acting on a single qubit. You can have more complicated cases, like for example, like this is a fancy control gate which is acting simultaneously on 4 quantum systems at the same time. Basically, you cannot decompose it into a Kronecker product of like 4 different operations. Okay, it's acting on that whole space at the same time. Okay, so your gates, your transformation, they can act on a single, they can act on many of them, 2 or more at the same time. And again, like look what I'm doing here. I'm just going with the control, and then I'm saying that the operation is x. This is control 1, so I'm just saying that like number 1 and number 2, if they are 1, act it. And then this is basically control 0. So like these are like the arguments for our control gate. And again, like if you don't know how to use like these functionalities, just look at our documentation. It has many examples, and each of these named operations, like they are explained here in detail. Whenever you are looking into the documentation, especially for circuit operator, please remember that many of the things that you see here, they are actually quantum operators. So if you go here, let me show it one more time. And under the details, you didn't see any description of the control operation. It means it is under the documentation for quantum operators. So let me just go at the very long documentation. So if we click on quantum operator, and here, like you would see it, like all these, all of them are a collection of control gates that we have here. So we can find like the detail here. Okay, so that's the one that I was using. And each of like these operations, they have a full name or they have a short name. Like you can use either one. Now let me just give you like a very specific example regarding like what we usually call as a quantum algorithm for a very particular goal. And I'm gonna use a textbook example, which is Grover quantum search algorithm. Okay, so the idea is like this. Let's say that we have this Boolean function, which is simple, the and then not on the second one. Using the other building functionalities in Wolfram Mathematica, you can easily find what are the solutions of this Boolean function. It's a trivial case. It is clear that if Q1 is true, Q2 is false, you will get that's a solution. You will get a true value for F. Okay, now let's what is a quantum process for finding this solution. Okay, so that quantum process is going to be like this. You would start by preparing your physical states in the ground state. You would apply some transformations, and then you would do a measurement. Remember, all of those transformations, at the end of the day, they prepare a very particular quantum state. So any quantum algorithm is like a very specific quantum state followed by the measurement. Remember, measurement, that's the only way that we can extract information out of our quantum system. For this very particular case, I guess you already noticed when I was showing you the documentation for quantum circuit operator, we have a long list of named operators, named circuits. So these are very common circuits that we have for a very particular algorithm. And let me focus on, again, as I told you, that's a textbook example, Grover search algorithm. Maybe it's better if I just show it to you that we have auto completion. So when you just type it, it shows you complete list of named operators, that named circuits that we have. I don't know, let's just look at the magic one for preparing Bell state, and that's what we have here. By the way, all these features, this gray box, that particular composition that you may not like it to see it on the top, all of them, you can easily customize them using our label functionalities. And let me just find it for circuit diagram. It's here. You see, what I did was, I just searched through the documentation, and that's the diagram for quantum framework. And these are all the details, all the options that we have for circuit visualization. I know, many of our users are using, Wolfram language for visualizations. So, we have lots of options. You can do a lot. But anyhow, let's move on. So the input, the argument here is basically that Boolean function. I'm just saying that, look, I'm looking for Grover search algorithm. This is a Boolean function, and this is a circuit diagram that we have. The first, step, the one, that is inside the gray box, for Grover search algorithm, it is usually called diffusion step. Oh my God, for a second, I forgot the terminology. And the second piece that you see here is amplification. So what's happening here, is and by the way, each of them, let's say that you are interested in just looking at the Grover diffusion and to see, did I block it a few seconds? Yes, so I'm, this will be functional very soon. Let me just make a note of that. I'll fix it very soon. But anyhow, each of these pieces, let me also check if we have the Grover. Let's see, is it the same case for phase diffusion? Oh. Okay, I have broken that, so I'll fix it in a sec. each of these pieces basically like you can extract it. You see like the named operators, they were there. But let's continue. So what's happening here is that during the first step, the gray box, we are saving the information about the solution in an ancillary qubit, and then in the second step we amplify the basically the amplitude of that very particular solution. Okay. uh the Grover search algorithm, like remember, like it has two features. This is the one which is based on Boolean oracle. There is another one which is basically Grover. Let's verify, show it separately without using the ancillary qubit. Okay, so there are, whenever we, when you are looking into the literature, there are two Grover search algorithms. One of them with ancillary qubit, with the other one without that. In one case, we are saving the solution in ancillary qubit. In the other case, we are saving the solution in the overall amplitude. Like, basically we are adding a negative phase in front of like, our superposition. Uh, Make sure like, you understand the difference between the two. But anyhow, like, let me just focus on, what's happening here. So first, I need to prepare my quantum state. So, and this is, basically the step for preparation. So what I'm doing here, I'll make sure that like, the ancillary qubit is prepared in state one. That's why like, I added a not state here. And then like, I add Hadamard, on all of them to have a sort of like, uniform superposition. And again, let's read like, the code here. And this is again, one of the other things that by design, we spend so much resources making sure that, the code is also readable. Not applied on the third one, and then we have Hadamard, a collection of Hadamard on three qubits. Uh, there is like, instead of like, this design, you can go like, somebody would say like, look, I want to do it like this. I want to say like, Hadamard is acting on oops, on one and two and three. So that's the same thing. Okay. Uh, Again, like, this particular design, like, it's maybe easier than this one, but anyhow, like, you can use, either one. uh, the second one, like, it's good because sometimes you may want to act, I don't know, how the mod only on some specific, qubits without and skipping some of them. Okay, so that's why, like, giving it as an order, maybe it's better than just giving it, in this form. But anyhow, like, that's our preparation. And now look what I'm doing here. So here is basically like, i'm I'm making a composition of some circuits. Remember, this is one circuit, this is another circuit. And look how it is done. I'm saying that, like, the notation that we have here is just for right composition. I'm just saying that, like, okay, start with, like, the circuit that I called prepare, and then Grover, and then measure qubit number one and qubit number two. And this is a circuit that I have constructed out of that. So again, like, remember, like, this is another way of, like, thinking about, like, composition. It's literally like, whatever operation you have, as far as, like, it is an operation. Remember, operation means transforming the quantum state. You can have, their quantum, you can have their, like, their composition. The first one is a quantum circuit. This is a quantum circuit. This is a, measurement operator, but you can, compose them together. Okay, so this is our circuit, and now I'm saying that, okay, this circuit is acting on, a ground state of qubit number one through qubit number three. You can say it explicitly like this. You can say that, we have three states, all of them are preparing quantum state zero. That's one way of, like, doing that. Or again, like, as far as you are dealing with the register state, this is sometimes what we call as a register state. And by the way, this is another way of, doing exactly the same thing. You can say go with the register state of three qubits. Okay, so this is the same as what we have here, the same as what we have here. Many times, like, if you see me or, other people that Wolfram do coding, in our framework, we go with the shorthand representation. But anyhow, do whatever way that you are more comfortable with. And because we had, like, the measurements, Okay, so the result, is an object which is quantum measurement. Okay, because again, like, we had, measurement operator here. You see here, like, that the double, horizontal line on the top, that's basically a classical wire. That's the wire that you're saving, classical information. And by the way, one more time, all the labelings that you see here, the label on the left, the label on the right, whatever you want, like, showing, like, the classical wire or not showing the classical wire, you can customize them whatever way you like. You can eliminate it, you can change the color, you can make it brighter, you can make it darker, like, you can do whatever you want. But again, let's see, like, I did, all this operation, and I did, like, a measurement. Now the question is, okay, so what? Now let's look at the, probability, distribution. So what I'm saying here is, just return the probability plot of the results. And remember, because we were measuring 2 qubits, each qubit 2 possible, outcomes, so the potential outcomes are 4. Of course, like, I'm kind of cheating. I'm using a simple example that, that shows you directly the result. Grover-Searle algorithm, it is usually more complicated than that. But anyhow, look at the outcome with the largest probability. Here is a very special case. With probability 1, you'll get the case that Q1 is in 1, Q2 is in 0. Now, let me remind you, what was the solution? The solution was the first one true, the second one false. 1 and 0, and that's exactly the solution that we obtain. Okay, so that's basically like, a very simple, quantum algorithm for a very specific, objective. And of course, like, there is a hot topic for any quantum algorithm is like, how much it is, better than, classical counterparts. Okay, so that's a completely different topic. Like, to be honest with you, I'm not an expert on that, but like, I understand it, but uh, I would leave it to especially like, mathematician or computer scientists with quantum expertise. Like, they can elaborate more on that. There are lots of, textbook on that. Let me just mention one other thing. Like, you notice, the way that I created my overall circuit was using this fancy notation and right composition, etc., etc. Okay, so you may have a different mindset. You may have, look, what I'm doing here at the end of the day, it is also like, a composition of bunch of circuits, and the circuit number 1 is prepared, the circuit number 2 is go over, and then I do measurement. So why not giving them as a list inside the circuit operator? Yes, that's you can do that, and you would get this result. The only difference is like, in terms of, visualization, because like, now you're feeding each one of them as a circuit. We just wrap it around like, that gray box, and the label on the top, like, it's basically the composition of like, whatever you do. But again, like, if you don't want to see these boxes, or if you don't want to see those labels, you can easily eliminate them. Okay, like, you can customize all of them. And of course, like, this, the result, it's going to be exactly the same as the previous one. Okay, so they're different only in terms of like, visualization. That was basically a very, simple introduction to, quantum computation using our framework. So the way that I want you guys to, like, those of you who are new to this field, is just think about like, a target state, and then a very particular way of, preparing that state. Keep that in mind. At the very end, you are always dealing with the measurement results. Okay, so it's a probabilistic, like, reasoning, if you want to think about it. Like, that's how we do it in quantum theory. And by the way, this is not the only paradigm to do quantum computing. The paradigm that I'm like, explaining here is what we usually call as a gate-based paradigm. And majority of like, quantum processing unit, the actual quantum hardwares out there, they are claiming that like, if we can trust them that they are quantum, but anyhow, it's gate-based. There are some companies that are offering like, a different approach. Like, for example, like, the D-Wave, like, for them is not a gate-based like approach to do quantum computing. In those cases, like for a very particular objective, you would design like a Hamiltonian, and then like that Hamiltonian, that very particular Hamiltonian would do the job for you. So it's a very completely different approach compared to like what we have here. In terms of like experimental, which one is better, which one is like that, I don't know. That's a question for the experimentalists, and we should wait and see like monitor the progress in experimental advancement of like quantum processing units. So that was basically like what I had prepared for today. So if uh, there is anything that has not been one more time, remember like you just need to install the packlet. After like installing the packet, if you do not quit your kernel, like the functions will be there. But if you quit your kernel, like yeah, you have to basically install the packet like, every time that you're quitting your kernel. And of course everything behind the scene is done like, yeah, it's classical, like we are doing a quantum algorithm on a classical machine. Okay, it's, you can, by the way, like we have it in your documentation. If you are interested, you can send your queries from a Wolfram notebook. You can send your queries to a quantum processing unit. You can use like either IBM quantum processing units. You can use anything that is available on AWS, and like just wait, like get your result, and then like do whatever processing you want to do with that.